Our second problem for Dalton's law is going to involve a little bit of something different. Our previous problem dealt with constant conditions, so there was no change during the course of that problem. Now this problem is going to involve a change, and that's pretty important. I call these tank problems, and these tank problems really do occur under changing conditions. Now, brace yourself before you actually take a look at this problem. Here it comes. Ah, it's a long one. Let's read through it a little bit. Two tanks are connected with a valve. When the valve is closed, one tank contains a sample of neon at 4.6 atm and has a volume of 3.3 liters. The second tank is filled with argon and has a pressure of 1.2 atm and a volume of 2.5 liters. Temperature is constant at 22 degrees Celsius. That's pretty important. When the valve is opened, there's our changing conditions, and the gases are allowed to mix between the two tanks. What are the final partial pressures of each gas? So again, the fact that we're saying that the valve is opened indicates that somehow conditions are changing. Now, all of the laws that we used previously are still available to us in this problem now that we're using changing conditions. So all of those laws that you learned that have the ones and the twos in them would be valid for this particular problem. Now, just simply reading this problem is kind of overwhelming. There's so many words, and it's kind of hard to know how you're supposed to proceed forward. So again, I kind of like to translate this information into something more visible, more visual, and something easier to digest. Since we're talking about a whole bunch of different kinds of tanks, I thought it might be useful to actually take the time to draw them. So this is what I see this problem looking like. I have one tank of neon on one side, one tank of argon on the other, and in between a valve that would keep them separate in the beginning, but when they're opened, allows them to mix. And it's this mixture of gases that eventually is going to let me use Dalton's law of partial pressure. All right, the second thing I'd like to do is to kind of unpack the information that they give me about each gas. So within the context of the problem, they tell me that my neon is at 4.6 atm and 3.3 liters, and that my argon is at 1.2 atm and 2.5 liters. The other thing I noticed too is that they tell me that the temperature is constant. That's enormous. It's a huge context clue. What that lets me know is that I should be using, under changing conditions, things with ones and twos, the constant temperature equation, and that gives me permission to use Boyle's law. This is really starting to unpack my problem. So if I want to have the final pressure of each gas inside of this tank, I need to start defining what are my initial conditions and what are my final conditions. So let's just focus in on the neon for right now. The neon in the beginning part of this problem is stuck in only one half of this container that has a pressure of 4.6 atm and 3.3 liters. Those are my initial, or ones, set of conditions. So I can start to fill in my Boyle's law equation, P1 times V1, and that looks a little something like this, 4.6 atm times 3.3 liters. Now I need to know what my final set of conditions are. And remember, we're trying to solve for its final pressure. So when we open the valve, the gas is allowed to expand all the way through the entire tank, which means its volume has changed. So when we go to fill out our P2V2, we're going to plug in X for its pressure, and its volume is going to be a little bigger than that 3.3 liters initially. It's actually going to be equal to 3.3 plus the 2.5 liters of the second tank, because that gas can expand throughout both tanks now. But now this looks like a math problem that I can plug and chug. So first I'm going to add together those two volumes and condense that back to 5.8 liters, and then do a little algebra to solve for X. And when I do, I find out that my P2 equals 2.6 atm. In other words, the partial pressure of the neon is 2.6 atm. That's one of the two answers that I needed for this problem. So I'm just going to list it underneath my neon gas. Time to focus in on the argon. And just like the neon, the argon is only located in half of the tank at the beginning of the problem. These would define our initial conditions. So 1.2 atm and 2.5 liters. So I can go ahead and fill that information in for P1 and V1, and it would look a little something like this: 1.2 ATM, 2.5 liters. And just like the neon, the argon is going to expand to fill both sides of the tank, taking up a whole new volume. We just need to know what the pressure is at that volume. So we'll fill that into P2 and V2. P2 will leave as X. V2 would be the combination of both volumes of the tanks, and that would be 3.3 plus 2.5. So just like we did before, I'm going to condense that down to 5.8 liters and then solve for my X, which comes out to be 0.52 ATM. That's the second answer that we needed for this problem. So that is the partial pressure of argon, and I'll list that simply under the argon tank. Now, what we didn't discuss is how Dalton's law actually figures into this whole scenario. A lot of the times with these problems, you'll also be asked, what is the final total pressure on the inside of both of these tanks once the valve is open? So in other words, the gases have mixed, the pressure is going to be the same throughout, but what is that pressure? Dalton's law helps us figure that out. So what is the total pressure inside of this tank after this change occurs? We'll apply Dalton's law. The total pressure has to equal the pressure of the neon plus the pressure of the argon, which luckily we've already calculated. So now it's a super duper simple plug and chug problem where we add up the two partial pressures to equal our total pressure of 2.6 ATM.